In this episode, we will talk about BLIP3-o, a family of fully open, unified, multimodal models. We're seeing, a really big push lately towards these unified multimodal models, systems that are designed to both understand and generate image content.
That's right.
And it brings up some pretty fascinating questions, doesn't it, about what are the best architectures, the best training strategies for these kinds of unified systems, especially when you get into the nitty-gritty of actually generating the images.
Indeed. It's a complex challenge. While we've seen multimodal large language models, or MLLMs, get really good at understanding visual stuff, integrating really high-quality image generation was still tricky.
Okay.
And this BLIP3-o research tackles that head-on. They're looking into different ways to represent images, different learning goals, different training strategies, all specifically for a unified setup. Their focus on mixing auto-regressive and diffusion models is, I think, a really key part we need to dig into.
Absolutely. And, what really makes this stand out for me is how thorough they were, and the fact that they've open-sourced everything.
Yeah, that's huge.
The code, the model weights, even the data sets they used for training and the instruction tuning bit, it's all out there. That kind of transparency is just so valuable for moving the field forward, right?
I totally agree. It helps everyone build on their work.
Okay, so let's start at the beginning. What's the real sort of fundamental reason driving this push for unified models that can do both understanding and generation?
Well, the main motivation really comes down to wanting more versatile and, frankly, more capable AI systems. When you embed image generation inside these MLLMs, the models can tap into all that knowledge they already have.
Yeah.
Their reasoning ability, how they follow instructions. They can use all that much more directly for generation. The paper gives a great example. You give it a prompt like an animal with a long nose. A unified model can just understand that directly. It gets the semantics. It doesn't need some separate step to rewrite the prompt or anything. It just knows what animal and long nose mean together and can generate from there.
Okay. That makes a lot of sense. It really streamlines things, doesn't it?
Exactly.
Instead of having separate models trying to talk to each other and translate things back and forth, you've got one system that understands and creates within the same representational space.
Precisely. And there's more to it. These unified models are naturally better suited for complex, in-context learning stuff.
Like what?
Think about iterative image editing. You start with an image, then give it text instructions like, make the sky bluer, or add a hat,
Right.
or imagine a visual dialogue. The AI isn't just answering questions about an image, it might need to generate a new visual element as part of the conversation. With a unified model, these kinds of interactions can happen smoothly. You don't need to switch modes or call out to some external tool. It's all integrated.
Yeah, that paints a picture of a much more kind of fluid and natural way to interact with AI. More like how we humans juggle different senses and information all the time.
Exactly. And maybe on a slightly deeper level, building these robust unified models is seen by many as a really critical step towards artificial general intelligence, or AGI.
AGI.
I mean, for an AI to be truly general, it needs to perceive, interpret, and generate all sorts of content, not just text. By getting models to reason and create across different modes like images and text together, well, we're moving closer to systems that can interact with the world more holistically.
Okay, the motivation is definitely strong. Now, the BLIP3 researchers, they were particularly interested in combining auto-regressive and diffusion models. You mentioned inspiration from OpenAI's GPT-4o.
Yes, that's right. I mean, the exact details of GPT-4 are kept under wraps, obviously. But its impressive abilities, understanding and generating images, editing them, it's led to what the BLIP3-o paper calls emerging hypotheses about how it might work internally. The leading theory, or at least a popular one, is that GPT-4o could be using a kind of hybrid pipeline.
Okay.
The idea is maybe an auto-regressive model processes the input first text, maybe visual cues too, and creates some kind of intermediate representation.
Right.
Then that representation gets fed into a diffusion model, which refines it and generates the actual image pixels.
So leveraging the strengths of both.
Exactly. Autoregressive models are great at context, sequences, reasoning. Diffusion models excel at producing those really detailed photorealistic images. So combining them can give you the best of both worlds.
So the BLIP3-o team sort of took that potential architecture as a starting point for their own investigation. And within that autoregressive plus diffusion idea, they focus on two specific questions. What were they trying to figure out?
They really zeroed in on two key things. First, What's the best way to represent images as continuous embeddings? Basically, how do you turn the picture into numbers the model can work with effectively?
Yeah.
They specifically compared using variational autoencoders, VAEs, versus using CLIP encoders. CLIP standing for Contrastive Language Image Pre-training.
Okay, VAEs and CLIP. Both ways to get a numerical version of the image, but based on different ideas, right?
Exactly.
Yeah.
VAEs are generative networks. They learn to encode images into a lower dimensional structured latent space, aiming to capture the sort of statistical essence of the image data, allowing for reconstruction.
Mm-hmm.
CLIP encoders, though, are trained differently. They learn from massive amounts of image-text pairs to grasp the semantic meaning. They try to put images and their descriptions close together in this shared embedding space.
Got it. And the second question?
The second big question was about how to best model the distribution of these continuous visual features after the autoregressive model generates them based on the text prompt. Here, they compared using a straightforward mean-squared error loss MSE loss against a more sophisticated diffusion technique called flow matching.
Okay, so it boils down to how do we represent the image numerically, and what's the best math, essentially, for training the model to predict that representation from text using this combined auto-regressive diffusion approach. Let's dig into the image generation part more. The paper talks about encoding and reconstruction first. Why is that step so critical?
Yeah, that encoding reconstruction piece is foundational. It's really about efficiency and quality down the line. The basic idea is you use an encoder network to compress the raw image pixels, which is a ton of data, into a much smaller, lower-dimensional embedding. This embedding should capture the important stuff about the image. Then a decoder network takes that compact embedding and tries to reconstruct the original image. Doing this helps because the generative model that comes next, like the diffusion model, doesn't have to work directly with the massive pixel space. It works with this smaller, denser representation. Makes training much more stable and, frankly, possible computationally.
Right. It creates a more manageable, information-rich version of the image for the later stages. And the paper looked at two main ways to do this encoding-decoding, VAEs and this combination of a CLIP encoder with a diffusion decoder. Let's start with the VAE approach. How does that fit in here?
So, like we said, VAEs map images into this continuous latent space. The key here is that the diffusion model they use for generation operates within that learned latent space.
Not on the pixels themselves.
Exactly. That drastically cuts down the computational load for training and running the model. So the process is, text prompt comes in, autoregressive model processes it, predicts a latent vector. The diffusion model then works on that latent vector, refining it. Finally, the VAE's decoder part takes the refined latent vector and turns it back into pixels for the final image.
Okay, so the VAE acts like a compression-decompression tool, creating a workspace for the diffusion model. Now, what about the other approach? Pairing a CLIP encoder with a diffusion decoder. That sounds interesting, since CLIP is usually more about understanding.
You're right, it is interesting. CLIP models, like the EVA clip they use, are really good at pulling out high-level semantic meaning from images. They learn what an image shows by linking it to text.
But they don't usually reconstruct images.
Not on their own, no. But the EMU2 model showed you can pair a CLIP encoder with a diffusion-based decoder to make an image autoencoder. In this setup, the EVA CLIP encoder turns the image into a fixed-length vector of these semantically rich embeddings. Then a diffusion model, maybe one already trained for image generation like Stable Diffusion, is fine-tuned specifically to reconstruct the original image from those CLIP embeddings.
Okay.
And a really crucial point here. During this fine-tuning of the decoder, the CLIP encoder itself is frozen. Its weights don't change.
Ah, so you preserve its understanding ability.
Exactly. You keep that powerful semantic understanding locked in. The diffusion decoder just learns the mapping back to pixels from that semantic representation.
So CLIP provides the what, and the diffusion decoder learns the how to draw it.
A good way to put it. And another key difference emerges here. Because this decoder is trained with a reconstruction goal trying to match the original pixels rather than just pure generation, the process during inference becomes deterministic. Meaning, if you feed it the same CLIP embedding from an image, the diffusion decoder will output pretty much the exact same reconstructed image every time.
Huh. That's different from the randomness we usually associate with diffusion models generating new stuff. Okay, so the paper compares these two methods, VAEs and CLIP diffusion. What are the main pros and cons they found?
They highlighted some important trade-offs. VAEs, generally speaking, are better at high-fidelity reconstruction. The images they reconstruct look very close to the originals, pixel-wise. Plus, VAEs are, well understood, readily available tech.
Okay.
CLA diffusion, on the other hand, offers a really big advantage in compression ratio. No matter how big the original image is, CLA-LIP encodes it into a fixed-length sequence of embeddings. They used 64 vectors in their experiments.
Always 64.
Yes, fixed length. This is really useful because it's consistent regardless of image resolution, and it's semantically dense. That can be really beneficial for the downstream models.
Compared to VAEs.
Compared to VAEs, where the size of the latent representation often grows with the image resolution. So VAEs might give slightly better pixel reconstruction, but C-light diffusion gives you this compact, fixed-size, semantically meaningful representation.
So it's a trade-off again, fidelity versus semantic compression efficiency. Okay, once you have these image embeddings, the next step is modeling them based on the text prompt using that auto-regressive model. How does that part work?
Right, so the user gives a text prompt. First, that text gets turned into numerical embeddings, standard stuff. Then, crucially, they append a special learnable query vector, they call it Q, to the end of these text embeddings.
A learnable vector.
Yeah, it starts random, but it gets optimized during training. As this whole sequence text embeddings plus the Q vector goes through the auto-regressive transformer layers, this Q vector learns to pay attention to the important parts of the text prompt, essentially distilling the visual meaning. After it passes through all the layers, the final state of this Q vector is the model's prediction of the intermediate visual features, the latent representation we've been talking about. The goal during training is to make this predicted Q vector as close as possible to the actual image features from the VAE or CLIP encoder that correspond to that text prompt.
So the auto-regressive model is like a translator, turning the text description into this predicted visual feature vector. Now, how do you train it to do that accurately? You mentioned mean squared error, MSE loss, and flow matching. Let's start with MSE.
Okay, MSE loss is pretty common and relatively simple. You have the predicted feature vector Q from the model and the actual ground truth image feature vector X. First, you usually put the predicted vector through a linear projection layer, just a simple transformation to make sure it's the same size, the same dimensionality as the target vector.
Right.
Then, the MSE loss is just the average of the squared differences between each corresponding number in the predicted vector and the target vector. Training tries to minimize this difference, pushing the predicted features closer to the actual ones.
Okay, straightforward. Minimize the difference element by element. Now, flow matching, you said that was more complex, diffusion-based.
Yeah, flow matching is definitely more involved. Unlike MSE, which basically pushes the prediction towards the average or mean of the target, flow matching tries to model the entire probability distribution of those image representations.
The whole distribution. How?
Okay, so for each training example of prompt Q and its matching image feature X1, you also pick a random time t between 0 and 1, and you generate some random noise xt, usually from a standard Gaussian distribution.
Noise, okay.
Then you create an intermediate feature xt by sort of blending the noise xc and the real feature x1 based on that time t. Think of it like a point on a path from pure noise to the real image feature. The diffusion transformer is then trained to predict the velocity, basically the direction and speed needed at that point xt to move along the path towards the target x1, all conditioned on the time t in the original text prompt Q. The training goal is to make the predicted velocity match the actual velocity required to follow this predefined probability flow.
Whoa, okay, so instead of just matching the endpoint, it's learning the whole journey from random noise to the target image representation guided by the text. That sounds like it could capture a lot more nuance.
That's the intuition, exactly. And it leads to a really important practical difference that the paper points out. When you train with MSE loss to predict these features, the resulting predicted feature Q tends to be almost the same every time for the same input prompt. It's quite deterministic.
Right, because you're just aiming for that single target point.
Precisely. And that determinism limits the diversity of the final generated images, no matter what decoder you use afterwards. If the intermediate step is always the same, the output won't vary much.
Makes sense.
Flow matching, however, inherently embraces the randomness of diffusion. Because it's learning this probabilistic path from noise, it can generate many different plausible image samples, even for the exact same text prompt. You get much more diversity.
Okay, but you mentioned it's more complex.
It is. Flow matching requires training this diffusion transformer, which usually means more parameters, more compute, compared to just adding a simple linear layer for MSE. They used a diffusion transformer, a DIT architecture, and found that making that transformer bigger did improve the image quality.
So it's that classic trade-off. MSE is simpler, more deterministic, maybe less varied. Flow matching is more complex, allows for diversity and potentially higher quality, but needs a bigger model. Okay, so the researchers tested different combinations of these encoding methods and training objectives. What were the main setups they compared?
They looked at three main combinations: CLIP embeddings trained with MSE loss, CLIP plus MSE, CLE embeddings trained with flow matching, CLIP plus flow matching, and VAE latent features trained with flow matching, VAE plus flow matching.
And they didn't test VAE with MSE.
No, they specifically excluded that one. Their focus was really on exploring these diffusion-based training objectives within the overall auto-regressive plus diffusion framework, and VAE plus MSE wouldn't fit that paradigm since it lacks the diffusion training part for the visual features.
Got it. 3 key setups. What models and data did they use for these initial comparison experiments?
For these tests, they used Llama 3.21b instruct as the auto-regressive model. The training data was about 25 million image text pairs from CC12M, SA1B, and JourneyDB. They used detailed captions generated by Alavi for the first 2 and the original JourneyDB captions for the third.
And how did they measure performance?
They used a few standard metrics: the Freshet Inception Distance, or FID score, on a dataset called MJHQ30K to look at the visual quality, the realism, and then J-Vol and DPG bench metrics to measure how well the generated images actually match the text prompts.
Okay, and what did the results show? Which combination came out on top?
Well, it's interesting. The CLIP plus flow matching setup scored highest on J-Vol and DPG bench, meaning it did the best job aligning the images with the prompts.
Okay.
But the VAE plus flow matching setup actually got the lowest FID score, which technically means the best score for visual quality according to that metric.
Huh, so a bit of a split result.
Kind of. But the researchers were quick to point out the known limitations of FID. It often captures style similarity more than anything else, and it doesn't always correlate well with human perception of quality or prompt following. They even mentioned testing OpenAI's GPT-4o on the same FID benchmark and getting a score around 30.0, which isn't stellar, showing that FID alone isn't the whole story.
Right, so considering everything.
Considering everything, they concluded that CLIP plus flow matching was the most effective overall design. It struck the best balance between really good prompt alignment and strong visual quality.
That's a really important takeaway. FID isn't everything, especially for prompt adherence. So even though VAE plus flow matching had a technically better FID, CLIP plus flow matching won out because it understood the prompts better. What were the main conclusions from this whole phase of comparing generation methods?
They boiled it down to 2 key findings. First, for putting image generation into these unified models, the auto-regressive part seems better at learning and predicting those semantic-level CLIP features than the more pixel-focused VAE features.
Okay, semantics win.
Yeah. And second, using flow matching for training does a better job of capturing the complex distribution of real images. This leads to more diverse outputs and, ultimately, better visual quality.
Okay, so CLIP plus flow matching is the winning combo for the generation part. The next step, then, is building the full unified model understanding and generation. They decided to stick with CLIP plus flow matching for generation. How did they approach actually unifying the 2 capabilities?
Right, since many understanding tasks also work well in that CLIP embedding space, using CLIP for both seemed like a good way to keep everything coherent. So then the question became, how do you train a model to do both? And they looked into different training strategies.
The paper mentioned joint training versus sequential training. Can you break down the difference?
Sure. Joint training is basically mixing everything together. You feed the model data for understanding tasks and data for generation tasks all at once, and you train the whole model simultaneously using some kind of combined loss. Models like Metamorph and Janus Pro do this.
Okay, learn everything together.
Right. Sequential training, on the other hand, is a 2-step process. First, you train the model, mostly, or only, on understanding tasks. Get that part working well. Then in the second stage, you typically freeze the main part of the model, the MLL backbone that does the understanding and reasoning, and you only train the image generation module, usually with text-image pairs for generation. LM Fusion and MetaQuery use this kind of approach.
Ah, so learn understanding first, lock it in, then learn generation. What are the pros and cons there?
Well, joint training could lead to some synergy. Learning one task might help the other. But it really depends on the data, the size, the ratio between understanding and generation examples. One task could easily dominate and hurt the other if the balance isn't right. Sequential training gives you more control. By freezing the understanding part, you guarantee you don't mess up those capabilities while you focus entirely on getting the generation module right. It avoids potential negative interference.
And BLIP3-o went with sequential.
Yes, they opted for sequential training. Which brings us to BLI3-0 itself. So building on CLIP plus flow matching and sequential training, what does the actual model look like and how do they train it? Okay, so they developed two main sizes, an 8 billion parameter model trained on a mix of proprietary and open source data, and a smaller 4 billion parameter one trained only on open source stuff.
Right.
Now, because there are already really strong open source understanding models out there, like the Qwen 2.5 VL models, they actually kind of streamlined the sequential process. They didn't explicitly do a separate first stage of understanding training.
Oh.
They essentially took the pre-trained Qwen 2.5 VL models as their starting point, their frozen backbone. For the big 8B BLI3-o model, they used Qwen 2.5 VL7B instruct, froze its weights, and then trained their diffusion transformer for image generation on top of it. That diffusion part had about 1.4 billion trainable parameters.
And the 4B model.
Similar idea, but built on the smaller Qwen 2.5 VL3B instruct as the frozen base.
Okay, so they cleverly leveraged existing strong understanding models and focused their training firepower on the generation module using CLIP plus flow matching. What about the diffusion transformer itself? What architecture did they use?
They based it on the LuminaNext model's diffusion transformer, or DIT. LuminaNext builds on the Next DIT architecture, which is known for scaling well and being efficient for text-to-image and other multimodal tasks.
Key features.
It uses something called 3D rotary position. Embedding helps it understand spatial layout, height, width, and the diffusion time step without needing extra position tokens. Each block uses sandwich normalization, basically RMS norm before and after the attention and feed-forward layers for stability. And they use grouped query attention, which helps make the attention mechanism faster and more stable in big models. It's a pretty efficient and robust setup for diffusion.
Sounds sophisticated. Okay, let's talk training data and the actual training process for these BLIP3-o models. 2 stages, right? Pre-training and instruction tuning.
Correct. Stage 1 was pre-training for image generation. For the 8B model, they used a mix, about 25 million open-source images from CC12M, SA1B, JourneyDB, plus another 30 million proprietary images. And importantly, the captions were key. They generated detailed captions for all these images using Qwen 2.5 VL7B. Instruct these captions averaged around 120 tokens long. Very descriptive.
Wow, okay.
To help it handle shorter prompts too, they also mixed in about 10% shorter captions, around 20 tokens, from CC12M. Each pair was formatted like an instruction. Generate an image based on this caption.
In the 4B model?
Same idea, but only using the 25 million public images with the same detailed Qwen captions plus the 10% short ones. And really crucially, they've released those 25 million detailed captions and 3 million short captions publicly. That's a huge dataset contribution.
That is incredibly valuable. Okay, that's pre-training. What about stage 2, instruction tuning? Why was that needed?
Well, after that massive pre-training, they noticed the model still had some weak spots. It struggled with generating really specific things accurately based on text prompts. Things like complex hue and gestures, certain common objects like specific fruits or vegetables, famous landmarks, they mentioned the Golden Gate Bridge, and also generating readable text within an image like a word on a sign.
Even with all that data?
Yeah, the pre-training data was broad, but maybe didn't have enough targeted examples for these specific tricky categories. So they did a focused instruction tuning phase. For each problem area, gestures, objects, landmarks, text, and image, they actually used GPT-4o to generate about 10,000 prompt image pairs, specifically targeting that weakness.
Using AI to generate training data to fix the AI.
Exactly. And then they added more prompts from JourneyDB and DLA3 to boost the overall visual quality and aesthetics. This resulted in a curated set of about 60,000 high-quality prompt image pairs. And they've released this dataset too, the BLIP3-o 60K instruction tuning dataset.
Wow, that's a really interesting targeted approach. Okay, so after all this, how did BLIP3 stack up against other big unified models on the standard benchmarks?
They compared it against a whole list. EMU2Chat, Chameleon, SeedX, VAE, LMFusion, Show-O, EMU3, Metamorph, TokenFlow, Janus Pro. Quite a lineup.
Okay, and the results, understanding first.
For image understanding, on benchmarks like VQAV2, MMBench, SeedBench, MMMU, the BLIP3-o 8B model basically achieved state-of-the-art. It got the top scores on most of them. So leveraging that Qwen backbone paid off.
Excellent. And image generation?
For generation, they used Genevol, DPDBench for prompt alignment, and WiseScore for world knowledge. BLIP3-o-8b got a high Gen Eval, 0.84, and a good Y score, 0.62, showing strong prompt following and knowledge. Its DBG bench score, though, was a bit lower than some others, like Janus Pro. But again, they noted that these model-based evaluations like DPG bench aren't always reliable and might not reflect human judgment, which is why they did the human study.
Right. And what about the impact of that 60K instruction tuning dataset?
Oh, it made a huge difference. They saw immediate, significant jumps in both prompt alignment and visual quality. It cleaned up a lot of common generation errors. And this led to another key finding. The model adapted really quickly to a kind of GPT-4o style from that tuning data, improving both alignment and visuals. And maybe counterintuitively, it learned better from those targeted AI-generated images for those tricky categories than just seeing more real images.
That is fascinating. AI teaching AI more effectively in specific cases. Okay, tell us about that human evaluation study you mentioned, comparing it to Janus Pro.
Right, to get a better handle on quality beyond the automated metrics, they compared BLIP3-o-8b against Janus Pro 7b using about 1,000 prompts from DPG Bench. They showed human evaluators pairs of images generated by both models for the same prompt side by side. The evaluators rated them on two things separately: visual quality, aesthetics, clarity, accuracy of shapes, and prompt alignment, which image better matches the text.
And the verdict.
The humans clearly prefer BLIP3-o. It won significantly on both visual quality and prompt alignment, with high statistical significance.
So the human judgment directly contradicted the automated DPG bench score, where Janus Pro looked better.
Exactly. It really highlights why human evaluation is still so critical in this space.
Yeah.
You can't just trust the automated scores completely, especially for something as subjective as image generation quality.
Absolutely underscores that point. Okay, given BLIP3-o strong showing, what's next for the team? What future work are they planning?
They're already working on extending its capabilities, moving beyond just basic understanding and generation towards more interactive tasks.
Right.
Things like instruction-based image editing, change the color of the car, also multi-turn visual dialogue, where you can have a back-and-forth conversation involving images and text, and something called interleave generation, where the model might output a mix of text and images in one response.
Very cool.
As a first step, they're focusing on image reconstruction, feeding an image in, encoding it, and seeing how well the generation side can reconstruct it. They also plan to collect more instruction tuning data specifically for these new downstream tasks.
It sounds like they're aiming for much more dynamic and versatile AI interaction. The paper also mentioned related work. How does BLIP3-o fit into the broader landscape?
Yeah, they situate their work among other recent efforts on unified models. They categorize them based on how they handle generation. Some use regression losses, like SeedX, EMU2. Others predict discrete visual tokens auto-regressively, Chameleon, Show-O. And others use diffusion objectives, Dream, LLM, Transfusion. They position BLIP3-o as the first really systematic look at the design choices within that hybrid auto-regressive plus diffusion approach.
Okay. Any specific comparisons?
They compare their sequential training strategy to LM Fusion, noting the similarity of freezing the backbone but highlighting that BLIP3-o uses a lighter weight diffusion head. They also mention MetaQuery, which also connects frozen MLLMs to diffusion using queries, but points out MetaQuery used VAE plus flow matching, while BLIP3-o found CLIP plus flow matching to be more effective.
Got it. So it builds on existing ideas, but carves out its own specific contribution in exploring that AR plus diffusion space with CLIP and flow matching. Okay, let's try and wrap this up. What are the absolute key takeaways from the BLIP3-o research?
I think the main takeaways are, first, this deep dive into combining autoregressive models and diffusion models for unified capabilities is really fruitful. Second, within that framework, using CLIP embeddings for semantic representation and flow matching for training the generation process seems to be a really effective combination, leading to faster training and better quality images. Third, sequential training, leveraging strong pre-trained understanding models, is a viable and effective strategy. And of course, they introduced BLIP3-o itself, a new family of state-of-the-art models, significantly boosted by that BLIP3 60K instruction tuning dataset focused on fixing specific weaknesses. And finally, the open sourcing. Releasing the models, the code, and those massive caption and instruction tuning datasets is a massive contribution that should really help push the whole field forward.
It really feels like a significant step forward, blending understanding and creation in a more integrated way. It definitely gets you thinking about where this is all headed, doesn't it? Yeah. The potential for these unified models to enable AI that perceives, understands, and generates more like humans do. It's quite profound. How these systems continue to evolve and what completely new applications might emerge. Well, that's definitely something to keep watching.